All right. Today we are going to finish our conversation about voltage in arc welding, and then we're going to discuss metal transfer. Next Tuesday, we are having quiz 3, and the topics for quiz 3 are everything we have seen up to today. That will include some parts of metal transfer. If you look at all the exams, you're going to see some questions about the heat affected zone, about some basic questions about metallurgy. That is what we start to discuss. You'll see questions also about voltage for sure, how to calculate a voltage in TIG or MIG, which we are seeing now. And also questions about metal transfer that you'll see. We discuss a little formula that helps us estimate if a process will be on spray transfer or globular transfer. All right. So, this is what we had seen last class, that in the most general case, we have an electrode extension, we have the arc length, and then we define some terms that are very important to have clear for us in the class, because the same words are used for different things in other places, like the Lincoln Procedure Handbook, and some other times the same things have different words. So what matters is the concept, not the names, but let's make sure that we are consistent within the class on what is what. So one is the contact tip to workpiece distance. This applies to every wire-based process: subarc welding, MIG welding, flux core, metal core, and is distance from the contact tip to the plate. There are subtleties. For example, if all of a sudden this is always the same, then we have the electrode extension, which is the distance between the point of electrical contact. In this case, I made it a little bit offset, but let's say that it happens right here at the tip. And from the point from the edge of the tip to where the arc attaches. And that's the electrode stickout. The Lincoln Procedure Handbook says that the electrode stickout is all from the contact tip to the plate. Not really true. Then the arc length. And although this drawing has nothing assigned for the part of the droplet, it's because in practice it's hard to pin down. So, and the arc length is the arc length. Here's the subtlety I wanted to mention just a second ago. If all of a sudden we have a weld that has a deep penetration and we have a big depression of the surface, all of a sudden the arc is longer, right? And that arc length is longer. So typically we would say arc length plus stick out equals contact tip to workpiece distance. But there are subtleties, right? If the penetration is deep, we might need to account for penetration too. And in all these things, we need to start keeping in mind. I'm gonna make a note to clean up the drawings for next time. Okay. So we saw that we have 3 main voltages that are the voltage of the anode fall, the voltage of the arc column, and the voltage of the cathode fall, which we discussed in deep detail in our class on plasmas. But in addition, we said we have more voltages than that. We have the voltage loss at the cables, the voltage loss at the contact tip because it's a sliding contact, and in addition, a voltage loss at the electrode stickout, which we have not discussed yet. But Alejandro used the concept on Tuesday's seminar. So about the arc, we already have these voltages, which are on one hand, extremely useful and pretty good predictors. On the other hand, I came up with these voltages based on my experience and talking with many people, but the moment I tried to justify them fundamentally, it got it's a lot deeper than I have told you, deep enough that I myself I'm struggling to come with pretty good justifications. But for now, we're going to be using these voltages that give us good results. We talked about how the leads have two effects. Not only the resistance that relates to the DC current. So, and if I were to have a bigger conductor, I would have lower resistance. But in addition, we have something called the inductance, that is some sort of resistance to the passage of pulses, or to the resistance to variations of current. And the consequence is that we can have some voltage loss due to resistance, which can be significant. For example, in this one example, numerical example we had all worked out, we saw that was 3.3 volts, which is high, and was equivalent of 1.3 kilowatts dissipated into the air. All right? And then we talked about the inductance, and we saw that the inductance had two components, one due to external fields and the other one internal fields. Internal fields related to skin effect, and it didn't really matter all that much. But we saw that inductance can play a huge role in blocking high frequencies. And for that reason, if you have a welding process that involves sharp pulses, for example, STT, you want to have short cables. If the cables are too long, you're paying for a machine capable of doing high pulses, but you are not getting the high pulses. You get the worst of both worlds. And we work through these numerically too. And here we have an example about how a square wave that, in theory, the square wave has a low frequency. In reality, the square wave is made out of a combination of infinite sines or cosines that have very high frequency. And as we chop off the high frequency components, we destroy our square wave, and we end up with something that is close to a sine wave. And all the sharp edges, that are good reasons to have the sharp edges, are going away. So a question out of intuition that I'd like to hear from you through the chat. If I'm running an AC process that has some positive current and some negative current, right? Which one do you think will have more arc stability? A sinusoidal waveform or a square waveform? Let's say for now we're talking with short cables, so the square is quite square. Which one do you think will have more arc stability? The sinusoidal waveform or the square waveform? Square. Aha, ooh. Well, we have 2 for 1. So somebody said square, somebody said sinusoidal. Good. Let's see. When we have AC, that means sometimes the current is positive, sometimes the current is negative. Mathematics tells us that at some point current is 0, right? And in a sinusoidal wave, we approach the 0 with some amount of slope, right? So the current it gets reduced as it crosses 0, and then it increases on the other direction, right? In the square wave, we cross through the 0 very quickly. So there you go, I agree. Square waveform is good for getting a stable arc. And that's one of the reasons why some, for example, we can, if you remember, we said we use 60-10 with AC machines and 60-10 with DC machines and 6011 with AC because the potassium is an arc stabilizer. That sounds good. So then how do you explain that we can use AC in processes such as MIG or such as TIG, right? In which we don't have an arc stabilizer at all, just the opposite. Argon had a huge ionization potential compared with potassium, right? How can it be? It is because we use square waveforms. If you try to do AC TIG with a transformer type of machine, it's likely not to work very well because as we approach zero gradually, the arc just extinguishes and doesn't start again. So you have to go very quickly through zero. Isn't this amazing? Like how things come together. 6010, 6011, TIG, square waveforms, transformer power sources. We have this little bit of understanding and we can explain so much and understand so much. Now, let me tell you, do you think you can do AC TIG with long wires, with long leads? Right? Of course not. The answer is that if we have long leads, we're gonna turn our square waveform into sine waveform. Now, if you don't know any of these things, you think it's just magic in action. Why one yes, one no? They have a cable, everything of the connection is good. But we understand, and we can make sense out of all these things. For example, if you want to have a pulsed waveform and you want to be away from your power source, what some companies do is to do the pulsing in a small unit that doesn't generate power, but just controls the power and is closer to the weld. So you have a big power supply, long leads that are pretty much running on DC, and then you have the pulsing unit close to the welding torch, and it's much smaller and more maneuverable. Right. Okay, so one of the questions is, why do they have other waveforms? All right. So we already discussed a square waveform that has this arc stabilizing phenomenon. When we talked about STT, we did talk about STT in our unit on MIG, right? And that pulsing was related to how to modulate the metal transfer. We're gonna get back into that today. Other pulses are related with the droplet. If you see the droplet has some oscillations, and that means it has a natural frequency of oscillation. So with different pulses, you can have different forms of heat input, but also different ways of exciting the resonant frequency. If you get the resonant frequency right, you can encourage the detachment of the droplet at lower currents, right? The engineering of waveforms in welding is amazing and is right today done mostly inside the companies, and they sell you waveform number 1, 2, 3, 4. You don't get to choose other than 1, 2, 3, 4. Some companies give the welding engineers the power of designing their own waveform. Now, sounds awesome, but with great power comes great responsibility. Do you know what you're doing? Typically you don't, among other things, because even if you took this class and you already joined the 0.1% of best welding engineers, you still need high-speed cameras to make sure that whatever pulse you design is working the way you meant. We have 3 of those in the lab. So come to the lab as soon as the COVID is over. So we talked about voltage loss at the contact tip because we have a sliding contact. And something I take for granted is that you know that resistance times current gives you voltage, and voltage times current gives you power, right? And so that's why constantly I'm talking about these milliohms of resistance. When I combine with current, I get voltage. And when I combine this voltage with the current, it gives us power. Extremely important, very basic. All right, so let's get into what we haven't discussed on the previous class, the stick out. the stick out is so important. The stick out is so important. For example, in if you read the Lincoln Procedure handbook, it will tell you the problems they had with high currents and stick electrodes, shielded metal arc welding electrodes, because the current is going through the whole stick, and sometimes the welding rod can get so hot, right, that the flux coating starts to peel off. So this we're discussing is very universal. Let's talk about MIG in, I'm focusing mostly on MIG, but the concept of stick out applies to stick welding too. So here we have our contact tip. Here we have our wire coming out. Here we have the droplet. And this, as the current goes through the electrode extension, we have a resistance. And the resistance is, we have a resistance that is current. We have a voltage loss that is current times resistance. So the voltage loss is current here, times the resistance is proportional to the length and inversely proportional to the cross-sectional area of the conductor. And the resistance, here we have this that is called a resistivity. I will tell you in a second why I call it effective. To those who took heat transfer with me last term, you might remember this exact same equation when we talked about thermal conductivity. And the thermal conductivity in something like a wall or in a rod, such as the electrode extension, was proportional to the length or the thickness of the wall, inversely proportional to the cross section. Same thing again. Now, the resistivity, that is a material property, varies quite a bit with temperature. In the case of steel, varies almost by a factor of 10. And guess what? Let's say right here between the droplet and the electrode, what is the temperature right here where my cursor is between the droplet and the stick out? Anybody wants to venture a guess for temperature there? Melting temperature, very good, but that's an easy guess. Here we have about room temperature. So in the stick out, the temperature varies from something close to 20 degrees, let's say, to 1500 degrees. And the resistivity varies a lot. In this formula, in reality, we should do an integral. Let me tell you, I've already done it. You do the integral, and we have written a super cool paper. And if you were to do the integral with this variable, and we also measure the resistivity, it's a big deal measuring the resistivity as a function of temperature. And I will recommend something that, again, is not exact, but it's a pretty good guess for the effective resistivity of steel, of ER7ES, to be this number I have here. Resistivity is higher with more alloying elements, because conducting electricity, the flow of electrons gets disrupted with all these different atoms in there. And so if you were to measure the resistivity of a base plate, say a 1020 steel or whatever it is, you'd measure a number. If you measure the resistivity of the wire you used to weld that, the resistivity is higher because the wire has more alloying elements, right? Has more manganese to suck up the sulfur or the oxygen, has more silicon often, right? Has a little bit of titanium to generate this acicular ferrite we like so much. For that reason, if you try to approximate resistivity using a tabulated value from a book for a random steel, you tend to be low. But we measured it for welding wires. And also here we have some values for aluminum, which this I got from tables because we never measured it for aluminum. So length of stick out, which is typically of the order of half an inch, but doesn't have to be, but typically is of the order of half an inch for MIG, for for subarc is longer. Effective resistivity, which is, we have this number here. We have the cross-sectional area of the wire, that if you know the wire diameter, you know the cross-sectional area, you know your current, and here you get, you know the current, and you get a voltage, right? And now, with the same wire, you can have a very large range of currents. Here, I'm gonna tell you a very rough approximation. As you realize by now, I like rough approximations. And I like rough approximations because my enemy is complete ignorance. When you know nothing, a rough approximation is awesome. When you go from rough approximation to an exact approximation, you might end up spending all the effort of a PhD and you gain 10% of accuracy. Some of our guys do PhDs, but not everybody does a PhD. So rough approximation is cool. So typically, when you want to have, you're running a wire with a current, and you start to increase the current, right? But if the current is too high, you should switch to a wire that is the next larger diameter. And if you keep increasing the current and it's too high again, you move to the next wire that has the next diameter. So overall, for a single wire, you can have many currents. But more or less, if you get the sweet spot for each wire, at what current each wire works best, you get that the current density in welding is of the order of this number I have here. 2.2 times, whatever it is, 2.2 times 10 to the 8 amps per square meter, right? It's essentially 220 amps per square millimeter, right, of wire. For this is a number that changes because for the same wire you can have different currents, but more or less, if I take this very rough value of cross-section, I would have current over current over cross-sectional area is more or less constant. Effective resistivity for steel is more or less constant. And I get that the voltage of the stick out is of the order of 4 volts per inch. Can be 2 volts per inch. It can be 8 volts per inch. But more or less is this value I have here. If I ask you to give me a voltage and I give you all the elements to calculate it here, I want you to do this calculation and give me a proper voltage. But if you're in the middle of Japan because you were kidnapped during a conference and you have to think on your feet very quickly, this number here is not too bad. You might be off by a factor of 2, but I prefer to be off by a factor of 2 than to be in complete ignorance. So this is quite powerful. Typically, the stick out in MIG is of the order of ½ an inch. So the stick out voltage loss in MIG is more or less 2 volts. Can be a little bit less, can be a little bit more. If I ask you to calculate it, you calculate it properly. But at the very least, you'll never be in complete ignorance. So this is a similar summary that we had before, but we expanded it. We have voltage loss in the leads, we have voltage loss in the contact tip, and voltage loss in the stick out. If I were to ask you about stick welding, the stick out is all the distance between the clamp and the end of the electrode. And as we consume the electrode, the stick out is changing. But here's the trick. In stick welding, the electrode is so thick that the voltage drop in the stick out of stick welding is very small. In MIG, it's not small. In MIG of steel. And I'll tell you more things. In MIG of steel, it's not very small. We talked about voltage, and I mentioned that voltage combined with current is power. And power is where the game is played, because power is what melts the plate. Power is what melts the electrode. power is what gets lost in the inefficiencies of the process. So let's use these numbers, which as discussed, and let's do a rough estimation of energy distribution in MIG welding. Let's think of an example, which could be anything, but let's say we have 200 amps DC electrode positive with a 12 millimeter electrical stick out. C5 means 5% argon with 5% CO2. And that's what way they call it. C10, argon 10% CO2. So let's go from top to bottom. In this case, we have a voltage loss at the contact tip, right? We said in the contact 2 milliohms resistance, 2 milliohms times 200 amps, that is half a volt. We have half a volt at the contact tip alone, and it's more or less 80 watts. 80 watts is not so little. If you ever have a 75 watt of the old school filament lamps, you don't want to touch it. It burns all right. It's a lot of power. Then we have the electric stick out, in which if you see here, I didn't give you a wire diameter. Maybe I should have. But if I don't give you a wire diameter, you can still ballpark it. Say more or less 2 volts. We can do better. We can do better. But in the absence of all other info, I'm going to call it more or less 2 volts. That means there are more or less 400 watts being dissipated in this wire, right? These 400 watts of electricity that are being generated in the wire, they help to melt the wire. Then we have the anode fall voltage, more or less 4.8 volts times the 200 amps. That gives us almost 1 kilowatt, right? But look at this, more or less 400 watts in the stick out, and more or less double in the anode. The stick out matters. So if I were to have a longer stick out, right? Say I somehow have the same current, and I have a longer stick out. Do you think the wire feed speed I need in MIG should be higher or lower? So same current, but longer stick out. Longer stick out means, should I have higher wire feed speed or lower? Higher, of course, because with a longer stick out, we have more resistance, and with the same current means I'm generating more power to melt the wire, right? We start having an understanding of what's going on, right? And stick out, especially in steel, is a very unfairly dismissed welding parameter. People know the current, people know the voltage, people know the wire feed speed. But you know what? In steel, if you don't tell me the stick out, you're giving me insufficient information. I'll show you how much that matters. And then we have the arc column, let's say 6 millimeters, and we using what we know about the voltage would be 4.5 volts, and that is about 960 watts in the arc. I'm making up something that is not horrible. I'm saying about 1/3 of those 960 watts come to melt to the plate, about 1/3, and about 2/3 are wasted. They go away in the form of radiation that gives you cancer, and in the form of hot gases, right? Of metal vapors and hot argon going around. And then we have the cathode fall, right? The electrode is positive, the plate is negative, it's a cathode, it's a non-thermionic cathode, and this is almost 3 kilowatts. That's a lot. in this case, we would be having good penetration because we're putting so much energy in burning the plate, and good deposition. Right? In total, this would give us just between the contact tip and the plate, 25.8 volts, which for those of you who actually know welding, you'll realize, yeah, it's a reasonable number. And this gives us 5.16 kilowatts, right, of energy used, and used from the electrical outlet, right? Of which 640 watts, these from the arc column, are lost, and gives us a thermal efficiency of the process of 88%, right? Because the energy in melting the droplet came here, the energy in the electrode stick out went to melt the droplet, and the droplet falls here, right? And whatever came to the plate, the energy in the plate is good, and 2/3 of the arc are wasted. This value of thermal efficiency is pretty much what is tabulated. But now, if you say, what happens if I have a longer arc, or if I change some things, you can anticipate how your efficiency is going to change. These calculations we're doing are not in books. They should be in books. They will be in books. Someday I'm gonna write it, but they are so powerful. Now, if we add the 5-meter reach for the leads, 5-meter reach means 5 meters to go and 5 meters to come back. So it's a total of 10 meters. The voltage in the leads would be 1 volt. I like this one. 1 volt is not a crazy number, and gives us that this welding process would be more or less 27 volts. And we can anticipate this just using this summary slide we have here. Powerful. In the case of steels, voltage affects current, right? For example, in MIG, you set the voltage, you set the wire feed speed, but you don't set the current. The current sets by itself such that you get that voltage for that wire feed speed. Look at this. Let's say we're welding happily in this image on the left. Say now that I increase the voltage. If I increase the voltage, the arc has most of the voltage. So in my imagination, every time we talk about voltage, I assume that the voltage happens, a change in voltage means only longer arc. It's not exactly true because the electrode stick out also play the role. But if you say higher voltage, that typically means longer arc. And so if we have a longer arc now, because with the same contact tip to workpiece distance, we have a shorter electrode stick out. And if I have a shorter electrode stick out, am I generating more or less heat in that electrode? Let's say the current is the same. For now, let's say that the current is the same. Am I generating more or less current, energy in this stick out that is shorter? So, yes, shorter stick out gives us less voltage loss, right? Here I have a comment that says shorter stick out will give you less voltage, so less energy, but it's less voltage at the electrode, right? So if it is less energy, that means we don't have enough energy to melt the wire. So the machine will increase the current. And guess what? People use this for closed loop control of torch standoff in MIG torches or flux core torches, right? You have the process running, and if all of a sudden you see that the voltage, that the current is increasing, you know that something is happening. Let me show you how it works, because it's quite amazing. let's say you're welding left to right, and let's say you have your plate is bent. So it's not that the plate got thicker, but let's say the plate has it is not uniform and is bent. So let's say the machine keeps moving as it was. All of a sudden, the contact tip to workpiece distance is shorter. If the workpiece to contact tip to workpiece distance is shorter, and the voltage is more or less the same because I set the voltage, that means the arc will be more or less the same, but my electrode stickout will be shorter. So my machine will increase current. And I can have an Arduino, and which is what we're trying to do in the lab. I can have a current sensor, pretty much anything that says, oh, current went up, so I should pull the torch back until it goes back to the current setting, and the torch has moved. And this is fantastic. When people are doing internal cladding with flux core electrodes, they need to put a very long boom that is very flexible inside the tube, right? And the way they regulate that, they change the standoff of the torch from way down, way at the tip of the tube, but they know if they are too close or too far because they are sensing the current in the process. Super amazing, super amazing. Let me tell you more. Nowadays, that everybody talks about additive manufacturing or 3D printing, there are machines, and we are very likely to have one of those in our lab, that they use MIG welding to make a 3D part. One of the biggest problems of additive manufacturing, especially in metals, is that the layer height is not constant. Right? The layer height, it can be irregular or can have different height of bead. You know how they detect that? They detect it using exactly this. That's a current patent. You could generate a patent like this now, right? They measure the current, and that way they know what their contact tip to workpiece distance is. All right, so let me ask you one more question. We said that in steel, in steel, the electrode stickout is more or less 2 volts, because we went through this equation and I generalized it with some common values. Look at this. Here is aluminum, right? And my question to you is, what do you think the stickout voltage would be in aluminum? I want a ballpark value. What do you think the stickout voltage would be? Say, wait, let me give you a hint. Resistivity of aluminum is more or less 1/10 of the resistivity of steel. Yeah, it's of the order of 0.2 volts. Now, look at this. In processes such as, in a technology such as this, I need to measure 2 volts more or less accurately. I think I can, despite the noise of welding. But if you ask me to measure 0.2 volts, that is what happens in aluminum, I cannot really. So these additive manufacturing machines that use MIG for make 3D parts, they have a control system that works in steel, but it doesn't really work in aluminum. Isn't this amazing, right? You have the same machine. Just put a roll of steel and the machine knows what to do. You put a roll of aluminum and the machine says, I don't know anymore. Just because of these differences in the resistivity of the electrode stickout. I'll tell you more. There are theories that say that, okay, here. let's say if in this case we have aluminum wire, how much energy do you think you would spend in the electrode stakeout? Right? It would be a tenth, again, would be like 40 watts, right? So the electrode stakeout in aluminum doesn't play much of a role in the energy balance. The anode fold will be more or less the same, would be 960 electric watts, give or take. But the electrode extension all of a sudden became from 1/3 of the energy addition to the wire would become 3%, right? Or very so steel and aluminum are very different animals. The physics are the same. It's just what the consequences of the physics are. Here we have a very interesting problem. I was involved in this. A local company was making overlays. In overlays, you want to add a material to a plate, for example, for wear resistance. But you don't want to dissolve your bottom plate because the material you put on top is very expensive. And if you start melting the bottom plate, you start mixing all the good material with all the cheap steel, right? So you want to reduce dilution. So let's say this is a subarc welding process now, which is what it was. What can you do? One of the solutions they found, which is amazing because it costs zero money, was the one here. So let me tell you something. We talk in this class as if it's normal about electrode extension and anode fault voltage. People in general don't know that. When in practice, a machine works and you make product you can sell, you pretty much like put super glue on all the bolts and say, nobody ever touches this. And then the engineer who somehow figured it out retires and becomes just magic at work. Nobody wants to touch it. Nobody dares to do anything. They pay the consultant big money. And this is what the consultant said. How about if you actually dare to touch the torch standoff knob and you move the torch a little bit higher, and let's see what happens. If the torch now is higher, and let's say the voltage is more or less the same, then the arc is more or less the same length. We can calculate it a lot better, but more or less, the arc is, if the voltage is more or less the same, the arc is more or less the same. We're gonna have the same bead width because we know that the width of the arc depended on the length of the arc. If I don't touch the length of the arc, the width of the arc is more or less the same, right? And now I have same wire feed speed as before and the same travel speed. So my mass balance, which we're gonna study in detail later, but if I have the same wire speed and the same travel speed and the same width of the bead, I'm putting essentially the same bead as before. But because the torch is farther back and the arc is the same, that means I have a longer electrode extension. If I have a longer electrode extension, I'm generating more energy in the electrode to melt my electrode. Then it means I need to lower my current to melt the same amount of material. And see what happens. Because the arc length is the same, the width is the same. Because the wire feed speed and the travel speed are the same, the amount of material deposited is the same. Therefore, my bead is the same as before. But because the current is lower, I have less penetration, and then I have less dilution. What do you think? This is amazing. Magic. There are other ways of doing this too. One of the ways they have speculated is variable polarity. If, for example, every time the electrode here is negative, I would have a cathode fault voltage that is 12 volts instead of an anode fault voltage that is nearly 5. So every time I'm negative, I'm putting more energy into the electrode. And even if I don't move my contact tip to workpiece distance, I would be putting more energy, therefore I would be having less current, therefore I would be having less penetration. A little bit of understanding and we can make sense of so many things. Now, if you have a DC machine that is unable to give you the square waveforms for alternate current, then first of all, if your machine is DC, you cannot do a variable polarity. If you flip the polarity, just make the electrode always negative, the arc tends to be unstable. If you wanted variable polarity in subarc welding, the arc is so big that it's more or less stable. Sometimes you can get away with a sinusoidal waveform in subarc welding, just because the arc is so massive that it takes longer to extinguish. Still, I do not advise that. But you can buy a machine that gives you a square waveform. You'll be paying pretty penny for that machine. Sometimes it's good. Sometimes, based on your knowledge, you say, hey, let's do this solution for free that is more or less the same. Pretty cool. All right. So